We've looked at coordinate notation in the past. In coordinate notation, we say that x and y map onto some new points x and y with some alterations. With reflection, we tend to reflect across either the y-axis or the x-axis, which makes one of them negative. If we reflect across the y-axis, we're making all our x's negative. If we reflect across the x-axis, we make all our y's negative. But these are just examples. That's why it's e.g. A translation shifts things. We can shift both horizontally and vertically. Let's say we shifted 9 to the right and we went down 2. Then the coordinate notation would reflect that we added 9 to x and subtract 2 from the y values. Lastly, a dilation. Remember, we can have an enlargement or a reduction. To do that, we need to multiply both x and y by a scale factor. If that factor is greater than 1, such as 3, we're going to get an enlargement. If the number is between 0 and 1, then we get a reduction. So 1/2 x and 1/2 y would be a reduction. Okay. For example, let's translate this figure with the following coordinate notation. xy maps to x plus 3, y minus 1. Try this on your own first, and then resume the video when you're ready to check your solution. Alright, that we're going x plus 3 and y minus 1 tells us to go right 3 and down 1. So if I look at A, I'm going to go right 3 and down 1. This gives me A prime at 2, 1. If I look at B, I'm going to go right 3 and down 1. So I get B prime at 2, 4. C, same thing. I get C prime at 7, 5. And for D, I get D prime at 7, 1. And there I have my red shape, where the red is an image, so A, B, C, D is the pre-image, and A prime, B prime, C prime, D prime is the image. I can see that my pre-image points are the A, B, C, and D, which have ordered pairs -1, 2, -1, 5, 4, 6, and 4, 2. My image points are A prime, B prime, C prime, D prime, which have ordered pairs 2, 1, 2, 4, 7, 5, and 7, 1. Because for all of these, I did x plus 3, y minus 1. Okay, next topic is isometry. And isometry is a transformation that preserves length and angle measure. Essentially means a congruence transformation. So an isometry is a transformation that is going to mess with our shape, but it's going to yield a congruent shape. Looking above, we see that the red and the black are actually congruent shapes. And in fact, all translations are isometries. Looking at our list above, here we go. Translations are isometries. So are reflections and rotations. In fact, the only one that's not is a dilation. Which brings us to our first new theorem, Theorem 9.1, which says a translation is an isometry.